Scientific importance and theories. The significance of this study lies in how it redefines the relationship between quantum physics and gravity. Hawking's original insight linked quantum processes to black holes using the event horizon as the key feature. The new work shows that an event horizon is not necessary. What matters is how sharply space-time is curved around an object. This broadens our understanding of where quantum-driven mass loss can occur. This result strengthens the conceptual bridge between general relativity and quantum field theory. In most circumstances, the two frameworks operate independently. Relativity describes large-scale structure while quantum physics handles microscopic behavior. Dense stellar remnants fall into the narrow region where both frameworks become relevant. Demonstrating that evaporation arises in these systems provides another example of how quantum effects cannot be ignored when curvature is extreme. Another important contribution of the study is its emphasis on density rather than object type. Black holes, neutron stars, and white dwarfs were traditionally categorized based on whether they formed an event horizon or supported matter through internal pressures. The new model places them on a continuum. The evaporation rate is tied to curvature, which is itself tied to density. This reorganizes how astrophysicists think about the long-term behavior of compact objects. The theoretical implications extend further. If all dense remnants eventually lose mass, the universe does not settle into a static configuration of cooling stars and dying black holes. Instead, it evolves continuously even after all conventional astrophysical processes have ceased. The study provides a baseline model for this universal decay without invoking speculative physics such as proton decay or exotic particle interactions. The research also creates new pathways for understanding quantum gravity by showing how quantum fields interact with realistic stellar curvature. The study offers a concrete scenario where both theories apply simultaneously. It invites deeper exploration into how rotation, magnetic fields, or more complex matter distributions alter these predictions. Although these additions will make the calculations far more challenging, they represent an important direction for future research. While this is ultimately a theoretical contribution, it refines our picture of the universe's distant future. It also emphasizes a broader scientific point. Even when an object appears stable, quantum processes operating on vast timescales can gradually reshape the cosmic landscape. Implications and what's next. The study's primary implication concerns the long-term timeline of the universe. Cosmologists once envisioned a distant future dominated by slowly cooling white dwarfs and an extended era in which black holes persisted for extraordinarily long periods. The new results revise this picture. Because all compact remnants gradually lose mass, the transition to a cosmos without stable structures occurs much earlier than expected. As neutron stars, white dwarfs, and black holes evaporate, the universe becomes increasingly simple. Over time, the radiation produced by these decay processes spreads out and loses energy as space expands. The final state is not a collection of silent frozen remnants, but a diffuse bath of low-energy particles filling an ever-growing volume. This does not change the direction of cosmic evolution, but it does change the pace. The study also introduces a unified perspective on the fate of matter. Rather than treating each category of compact remnants separately, the model shows that they all follow the same ultimate trajectory. Once the mass loss becomes significant compared to the object's total energy, evaporation accelerates and the object disappears completely for the universe as a whole. This means that its final constituents are temporary. Another implication lies in theoretical physics. This work highlights that quantum effects can have meaningful consequences in gravitational environments long after conventional astrophysics has ended. It demonstrates that quantum field theory and curved space-time is not just a mathematical curiosity but a framework capable of producing concrete predictions about the universe's future. Looking forward, there are several directions researchers may pursue. One area is to incorporate more realistic stellar properties. Neutron stars rotate rapidly, possess layered interiors, and host extremely strong magnetic fields. These factors influence curvature and may alter evaporation rates. White dwarfs vary in composition and structure, which could also affect predictions. Another direction is to explore whether dark matter participates in similar quantum curvature interactions. If dark matter forms compact objects or dense clumps, it may also experience long-term mass loss, further reshaping the universe's final inventory. A broader open question concerns the early universe. Since curvature was far stronger shortly after the Big Bang, these quantum processes may have played a subtle role during that era as well. Although this is speculative, it offers an intriguing avenue for connecting the universe's beginning with its end through the same physical mechanism. Overall, the study reframes the future of the cosmos as an ongoing gradual process where quantum physics continues to operate long after stars, galaxies, and black holes have faded.